Assalamualaikum to our lecturer, Surveyor Zafika Aida binti Bidin. In this video, we are going to discuss about the soil improvements and stabilization techniques used in TRX and one vendor-built projects. Our group members consist of Cynthia Debbie Anadian, Claudia Nading, Nur Fatiha Shuhada binti Abdul Taib, and Nur Fitriana binti Jeffren.
Hello, my name is Claudia Nadi, and I will explain about the background of the building that we use for soil improvement and stabilization technique. The first building is Tun Razak Exchange or TRX is a 7-acre mark development aiming to position Malaysia as a global financial hub. The building was led by TRX citizen Dian Berhad under the Ministry of Finance. TRX also integrates Grade A offices, luxury retail, residence hotels, and the iconic Exchange 106, one of the Southeast Asia's tallest towers. The site of this building is as a former tin mine posed major geotechnical challenges including soft clay, loose sands, and mining cavities. The engineer used preloading with vertical drains, deep cement sinks (DCMs), and bored pile to bedrocks. This was used to ensure stability for heavy structure and deep basements. As for the parties involved, TRX is built on collaborations from Lendlease, a company from Australia that developed the TRX with mall, hotel, residence, and park, while Mulia Group from Malaysia built the Exchange 106 skyscraper. And for this building, there is no specific contractor since many parties involved in these constructions. And as you can see in the picture there, financial anchors like HSBC Malaysia, Evin Group, and Prudential Malaysia are setting up their HQ there. And last but not least, as for infrastructure and sustainability, the supporting works are led by IJM groups as a major infrastructure, Veolia as utilities, energy and waste management, and WCT Holdings as contribute roads and utility system. Next building is One Vanderbilt. This is an engineering a super tall landmark. This building was completed in 2020 and has a 93 story, 427 meters skyscraper rising beside New York historic Grand Central Terminal. The project faced tough site conditions where this building is built on glacial till and decomposed rock with irregular soil strata and close proximity to all infrastructure. Risks included groundwater intrusions and soil collapse. As for stabilizations and foundation solutions, the engineer used underpinning, slurry walls, and rock anchoring, where they also used jet grouting and soil freezing during excavation. The tower also stands on caissons, reinforced footings, and safely transferring loads to bedrock. This building was developed by SL Green Realty Corps, and the key collaborations included KPF as architect, Tishman's Constructions as a mains contractor, and one when the build is um, various of designs, engineering, and coordinations by blending super tall innovations with sensitive integration into Manhattan's urban fabrics. And that's all for this second building.
Hello everyone. In this part, I'll be presenting on several advanced ground improvement and foundation techniques used in major construction projects, specifically referencing their applications in TRX and One Vanderbilt. These methods are essential for tackling poor soil conditions and ensuring structural stability. Let's begin with three key ground improvement methods. Deep soil mixing involves blending soft or weak soils with cementitious materials to form soil cement columns. This improves load-bearing capacity and reduces compressibility and permeability. It was applied in both TRX and One Vanderbilt. Next, PVDs with preloading or prefabricated vertical drains with preloading are used to accelerate consolidation in soft soils. This speeds up construction timelines and helps reduce long-term settlement. TRX also utilized this method extensively. Lastly, vibro replacement. This method installs vertical columns of compacted gravel or crushed stone into the ground. It is suitable for cohesive soils, organic materials, and loose sands. It was implemented in the TRX development to improve soil stability. Moving on to more specialized techniques, jet grouting is ideal where traditional methods fall short. It uses high-pressure jets to break up and mix the soil with grout, forming strong columns underground. TRX used this method in areas where precision and adaptability were crucial. Next, dynamic compacting is a technique that improves the density of loose granular soils by repeatedly dropping heavy weights. It helps to mitigate risks like liquefaction and was employed in TRX prior to construction to enhance bearing capacity. Micropiling and board piling are deep foundation systems used when dealing with restricted spaces or vibration-sensitive environments. Micropiles are typically less than 300 mm in diameter and are reinforced with steel and grout. These were used in TRX to handle challenging soil profiles. Furthermore, the massive Met foundation is used in One Vanderbilt is a large thick-reinforced concrete slab that spreads the building's load over a wide area. It is particularly effective in preventing differential settlement where soil conditions vary. Next is the perimeter spread footings. They are shallow foundations built around the outer edges of a building. They reduce bearing pressure and help avoid excessive settlement, and were also used in One Vanderbilt. Lastly, basement excavation retention and groundwater control is vital when constructing deep basements. These systems stabilize vertical excavation walls and prevent collapse, while also controlling groundwater inflow. One Vanderbilt utilized these systems to maintain safe excavation during construction. In this part, I'm going to talk about the materials used for the soil improvement and stabilization. At the TRX site, one of the primary methods for soil stabilization involved the use of revolving blades. These blades were used to mix in-situ soil with a cement slurry, typically made from ordinary Portland cement, and water. To improve durability and environmental performance, additives such as fly ash, slag, or bentonite were also incorporated. These additives enhance the long-term performance of the treated soil while minimizing environmental impact. Another crucial material was polypropylene, which was used to construct prefabricated vertical drains, or PVDs. These drains were essential in promoting water drainage from soft soils and preventing clogging. In addition, granular fill was placed on top of the ground to provide weight, promoting consolidation by encouraging the release of pore water through the vertical drains. This step was critical to speeding up the settlement process in the marine clay layers found at the site. For areas with extremely soft soil, high-strength concrete piles were used to transfer loads to deeper, more stable soil layers. Next, vibrating probes were employed to improve both drainage and the load-bearing capacity of loose soils. In jet grouting, air and water jets played a key role. These jets crushed and mixed the soil, allowing cementitious material to be injected to form hardened columns underground. Lastly, huge steel weights were used for dynamic compaction, essentially dropping heavy loads repeatedly to compact granular soils and increase their density. Now, moving on to one Vanderbilt. Here, the use of cement-based grout was crucial for forming strong, impermeable soil columns. This material increased strength and reduced water permeability in the soil. To ensure structural load transfer, anchor bolts, steel reinforcement, and steel plates were embedded in the massive mat foundation, reaching down to more competent soil or even bedrock. Reinforced concrete was used extensively to handle both vertical loads and lateral pressures from the surrounding soil and structures. Additionally, steel rebar cages were installed to retain basement excavation walls and regulate groundwater, especially during deep excavation work.
Hello, my name is Cynthia Devi. I'm going to present about problem, solution, and the recommendation. But firstly, I'm going to present about problem and solution. The TRX in Kuala Lumpur faced big challenges because the ground was made of soft and weak soil like clay and peat. This type of soil can't hold heavy building well, so engineers had to improve the ground first. They used special methods like deep soil mixing, which adds cement to make the soil stronger, and vibro compaction, which shakes the soil to make it tighter. This helps to prevent the building from sinking over time. On the other hand, the one Vanderbilt building in New York was built on strong rock, but the rock wasn't even across the whole site. The building was very close to the Grand Central Training and train tunnels, so the work had to be done carefully. Engineers used slurry walls filled with special liquid to keep the soil in place while digging, and they also used anchor to hold everything steady. At the same time, they also had to pump out a lot of water to keep the area dry during the construction. At TRX, even after the soil was improved, engineers keep checking for any ground movement by using tools like settlement plates in New York because space was tight and close to the old building. They used ground freezing to safely work near train lines. Meanwhile, for the solution, the TRX project in Kuala Lumpur had soft and weak soil, like clay and sand, which couldn't support heavy buildings. Engineers used deep soil mixing and vibro compaction to make the ground stronger. They also used the drain and preloading to remove the water and also reduce for the future sinking. This helped to support tall buildings and underground structure. At one Vanderbilt in New York, the challenge was building next to subway tunnels and uneven bedrock. Engineers used slurry walls and rock anchor to keep the ground stable during the deep digging. They also did careful blasting to remove the hard rock without damaging the nearby buildings. Both sites had water problems. TRX used deep wells and pumps to keep the ground dry. One Vanderbilt had a strong water control system to protect the nearby tunnels. To stay safe, both projects used the real-time monitoring tools to track ground movement. They also used smart foundation design. Furthermore, I'm going to explain about the recommendation. One key recommendation for future construction projects is to do better and more localized soil study early in the planning stage. By using tools like silicon penetration test and geophysical survey helps engineers to understand the soil and groundwater condition more accurately. This could reduce the risk and avoid delays or unexpected problems during the construction. Another idea is to use more eco-friendly soil treatment method. Right now, cement based on ground improvement like in TRX create the high carbon emission. In the future, we can use greener material like geopolymers, fly ash, or new technique like microbial induced succulent precipitation, which are better for the environment but still effective. Also, there should be better coordination between soil data and building design by using tools like 3D models, finite element modeling, and also building information modeling. Engineers can simulate the ground movement and building roads in real time. This also helps to spot the problem early and adjust the design before issues happen on site. Lastly, the government and engineers should need to do the stricter rules and also standards for soil stabilization, because this includes to making sure the material and method meet the high quality standard and having regular site check. Next, I'm going to present about effectiveness and efficiency. Firstly, regulatory planning was a very different. One Vanderbilt in New York had to go through complex zoning rules and negotiate air rights due to its location next to Grand Central Terminal. In contrast, TRX in Malaysia had fewer restrictions and faster approval under centralized planning, which made the coordination more easier. Next, the site conditions were also quite different because one Vanderbilt faced the tight space and had to protect existing subway and tunnels during the construction. Meanwhile, for TRX was built on a more open and plain site. For the foundation, work was more simpler and less risky. In terms of technology, one Vanderbilt used advanced tools like the BIM and digital twins throughout the whole project life cycle. TRX also used BIM, but mainly for clash detection. The US market had more digital integration overall. When it comes to logistics, one Vanderbilt dealt with strict delivery schedule network and heavy traffic in a dense city. Meanwhile, for TRX had more space for stage and transport, which made the construction flow smoothly with fewer delays. For sustainability, one Vanderbilt achieved LEED Platinum certification, used local material and connected directly to public transit. Meanwhile, for TRX, it focused on building a green district with features like energy efficient system and water recycling. Through one Vanderbilt had stronger public transit links. Lastly, cost and financing were different. One Vanderbilt cost over $3 billion and relied on private funding and city incentive. TRX had stable funding from a government-linked company which helped to control the cost and align the project with national plans.
Now we move on to the construction techniques. For the Tun Razak Exchange (TRX) in Kuala Lumpur, the challenging ground condition mainly soft silty clay and loose sandy soil. So it required intensive soil improvement. Here is 3 main construction techniques that apply to improve this. So the first one is the deep soil mixing (DSM), where heavy-duty augers were used to drill and mix cement slurry with in-situ soft soil, creating deep soil cement columns. And then this column improved the load-bearing capacity and reduced settlement. DSM was applied systematically beneath the tower footprints and the basement zone. The next one is the jet grouting. High pressure cement ground was injected into the soil to break up and mix the surrounding material, forming solidified columns and panels. This method provided waterproofing and excavation stability, especially around deep basement and utility corridors. So the last one is the dynamic compaction, where to densify loose, granular fill near the surface, heavy weights were dropped from the height in a grid pattern. Then the repeated impact compacted soil will enhance the bearing strength and minimizing post-construction settlement risk. At One Vanderbilt in New York, the construction was executed on a complex urban site with glacial fill, shallow bedrock, and adjacent historic structures. So 3 key foundation and soil retention techniques were used. The first one is the slurry wall construction, where the deep trenches were excavated around the site and filled with bentonite slurry to stabilize the wall. Reinforced concrete was then poured to form permanent diaphragm walls. This retained the surrounding soil and controlled groundwater during deep excavation. So the second one is the mat foundation, a thick reinforced concrete mat, several meters deep, was poured across the entire building footprint, and then it distributes a skyscraper's massive load evenly onto the underlying bedrocks. Then this will minimize the differential settlement and enhance structural stability. The last one is the rock anchors, where the steel anchors were drilled and grooted deep into the Manhattan schist bedrock, and then this provided additional resistance to uplift the lateral force, especially important due to nearby subway tunnels and Grand Central Terminal. The anchor securely tied the foundation into the geological base. Moving on to the testing and monitoring, for TRX Kuala Lumpur, to ensure the ground at the TRX was properly stabilized, 3 key testing methods were conducted. The first one is the unconfined compressive strength UCS test, where this laboratory test was used to evaluate the strength gain of deep soil mixing DSM columns over time. It confirmed whether the soil cement mixture has sufficient load bearing capacity after curing. The next one is the California Bearing Ratio CBR test, where the CBR test assess the strength of compacted subgrade layers, especially areas intended for road and pavement. It helped determine the soil resistance to penetration under load. The last one is the plate load test, where this field test stimulate the pressure that would be applied by building foundations. It was used to directly measure the settlement and stiffness of the treated soil under structural loads, ensuring it could support high-rise development safety. Now we look after the testing and monitoring at the One Vanderbilt in New York City. Given the complexity of the site and its proximity to Grand Central Terminal, one vendor built employed advanced testing and monitoring technologies. So the first one is the UCS test and core sampling, where after the deep soil mixing, DSM soil column were extracted and tested for unconfined compressive strength in the lab. Core sampling ensured the uniformity of strength and binder distribution across the treated zone. So the next one is the shear wave velocity and spectral induced polarization SIP, where the shear wave velocity testing measured. Now we look after the testing and monitoring at the one Vanderbilt in New York City. Given the complexity of the site and its proximity to Grand Central Terminal, one Vanderbilt employed advanced testing and monitoring technologies. So the first one is the UCS test and core sampling, where after the deep soil mixing, DSM soil column were extracted and tested for unconfined compressive strength in the lab. Core sampling ensured the uniformity of strength and binder distribution across the treated zone. So the next one is the.
To sum up, the comparison between TRX in Kuala Lumpur and one Vanderbilt in New York is not just about their engineering, but also about their city planning, economic goals, and also environmental values. TRX was part of Malaysia Master Plan to turn Kuala Lumpur into a global financial hub. It also focused on modern design and green space and also sustainable infrastructure. One Vanderbilt, on the other hand, represents the New York vertical growth and its mixing of cutting-edge architecture with strong transport integration, especially near the Grand Central Station. While both towers reflect their country's ambition, they were built in very different urban settings. TRX was developed on underused land, allowing for the better control of layout and green feeders. One Vanderbilt was built in a busy, historic area requiring the advanced construction method and also extra care for the protect surrounding structure and transport system. Each project has its own unique challenges because TRX had to deal with soft soil and deep foundation. Meanwhile, for the one Vanderbilt had to zoning holders and tight logistics in a denser urban area. In the end, both skyscrapers show how architecture can adapt to different environments. Through their design and strategic vary, TRX and one Vanderbilt both stand as modern icons, showing what's possible when innovation, planning, and context come together. This project will help to inspire for the better building practices, smart city policies, and greener solutions for the future urban growth. That is all from our group. Thank you for listening.